Let's say you were given a collection of numbers in a matrix and you were told they were a bunch of differences or distances or similarities between observations, and the nature of the observations is not something you know. It may even be something you can't know, in the sense that the observations might have been kind of opinions, not especially quantitative to begin with. You can imagine a lot of reasons for wanting to translate that collection of distances or similarities, or whatever you want to call them, into a quantitative matrix of observations like we've been using in most of the other lectures. And today's lecture is about how you might go about doing that. What are the challenges? What are the kind of advantages to different strategies? And we're going to introduce a particularly famous strategy for doing this, for going from the distances to the observations, that's known as classical multidimensional scaling, which is a big name, but it's a relatively simple strategy. And we'll tell you the technical details about how you build that strategy in this lecture today. In the next lecture, we'll do some examples and see how you can actually put it to use. But today's lecture is about where does this method come from, and what is its origins, and how does it work? All right, let's get started. We're going to talk about something called multidimensional scaling, or MDS. And it's a collection of methods, so it goes by MDS sometimes. So it's a collection of different methods, and today we're going to see one of them. I just want to sort of dive right in and start discussing what multidimensional scaling is all about. The general premise of multidimensional scaling is that you're starting off with some distance matrix. All right, so let's suppose, which we described in the last chapter, last few lectures, or last lecture. So suppose you start out, suppose you've been given some kind of distance matrix that's n by n. And we'll call it D, just like we did in the last lecture, the last chapter. But we'll end up using multiple distance matrices in this, and so it's important to kind of remember which one is which as we get more and more of them. But so suppose that D is the one that you start off with, and so the idea behind this distance matrix is that in some way, Dij, so row I, column j of D, somehow quantifies some sort of distance from between two observations. So let's say it's even directional, maybe. So from observation I to observation J. So that's what the distance matrix quantifies in some way. Now, let's think about kind of what do you actually know? What does this mean you know? So here are the knowns. You know the number of observations, right? So the number of observations that's going to be n, right? So there's n different observations that went into constructing this. But there's quite a lot that you don't know about the observations. So you don't know, or unknown, and maybe even sort of unknowable. And that's what we're going to try to find out, sort of. That's what we want to try to investigate. So maybe it's even unknowable, the following different things. So you don't know what distance measure was used. I mean, you could, but let's just suppose that you don't. You don't generally know this. And if you definitely don't know the n by p data matrix. Of all the different observations. So we've always called that x. And so for that, like, observation I is row I of x. And we call that lowercase I vector. So you don't know that matrix. You don't know its rows, and more kind of worrisome, I think, or I don't know, maybe it's exciting. You don't even know p, right? You don't even know the number of features or variants or columns. You see, I think this is a point in the content where students sometimes get a little bit, I'm not sure if confused is the right word, but it can certainly be the case that that nobody knows these things, that the distance matrix came somehow to be in a way that there never was a data matrix X that it came from. And what multidimensional scaling is about is trying to kind of understand what sort of data matrix could go along with this distance matrix, or, you know, what would be a good one? Is there some good one with a small number of variates, p, or do you need to have a large number, or what is the story here? So this is kind of what multidimensional scaling is about. And so let's just try to, and I just want to mention here, in the book that I suggested, Everett and Hawthorne, they use a different letter for p. They use lowercase m. So if you're reading that, just a reminder for how to translate some of these things. So how is this unknowable? Okay. How could this be unknowable? Like, didn't somebody, isn't it, it seems sort of, I think, it always seems to me like you would think, so somebody had to have made this distance matrix somehow. Maybe they didn't use Euclidean distances, they used something exotic or something, but surely it was made somehow. And the thing is, sometimes it's just made directly. And so here's just a little example of how this could come to be. Right, so here's the example. The DIJs, the elements of the distance matrix, they might actually just be opinions. Like human opinions. Right, so imagine, for example, somebody made, I don't know, maybe they started with a similarity matrix, Sij, and they said, they gave a survey to a bunch of different lecturers in the stats department, say, and they say in this survey, on a scale of 1 to 10, how similar are students I and J? And so with that kind of question, you know, you might get different responses. Okay, and then let's just say that Dij is this complement distance. And so let's say it's defined in this case as like 10 minus Sij. So if the people have a similarity, the students have a similarity of 10, that's the biggest, then you say the distance between them is 0. So this is just a constructed example, right? So imagine if this question were asked, how would the different lecturers respond? Well, some of them would probably just go to their records and look at the marks that the students earned for different things, exams or projects or whatever, and then do some calculation and just get a number, and then they'd scale it from 1 to 10. I mean, we're math people, we probably would do that. But maybe some people don't do that. Maybe they just have some strong feeling about the students. Maybe it's totally unjust, or I don't know, or maybe they're geniuses. They have some amazing way to understand students. And so they might have a whole bunch of different schemes for how they actually answer this. And it doesn't really make sense to say that there is for sure some concrete X matrix that went into the building of this collection of distances, the differences between the students. And so this thing is it's like disembodied from any kind of data matrix X. And so what we want to think about with multidimensional scaling is when you're in that situation, how do you create a data matrix X out of the distances in some sort of a useful way, right? And so let's just say, and I'll comment that just as sort of a lingo thing, the initial, because of this sort of weird ambiguity, that it's not even clear that these distance is the right word here. So because of this, if your initial distance matrix or the given matrix is D, because of this ambiguity, sometimes your initial or given matrix D for us is called the matrix of dissimilarities or the matrix of proximities. I mean, those words don't really mean anything different from distance particularly, but it's just used to indicate where you started from. So it's called a matrix of, I think Everett and Hawthorne call them proximities. The idea is to inspire some kind of picture that like, oh, but this isn't not exactly a distance. What is this? Or some people call them dissimilarities. Which is maybe the right way to call them in this case because I computed them from similarities. So suppose this is the case. So what is the goal of multidimensional scaling? Right. So multidimensional scaling's goal it's somewhat simple, at least easy to kind of write down. It's to find some scheme for going from D to X. Including some mechanized way or a way to find or to pick or to choose the best P. Right, so we don't even, with this kind of ambiguous origin of the distance matrix where there's no data matrix that it really came from, you don't even know how many dimensions you should use. So like maybe Professor X just looks at one exam and then that's all he uses. So there's one-dimensional space that person used. But then maybe Professor Y had tons and tons of data. I have all these exams, all these projects. I've been monitoring how often they watch my Panopto videos. I have all these different ways to measure them. And so maybe for that person, it's like a 10-dimensional space. But so, what is the best P for kind of describing the data matrix here? And so in a way, you should see right away, this is sort of a little bit like principal component analysis, where you've got some matrix and you want to somehow view it in some space and you want to know the right number of dimensions to use for that space. Or I don't know if the right number is the right term, but like somehow the ideal or best way or best number of dimensions. So I'm just going to make a remark on a couple of pitfalls, and then we'll go into some of the details. So pitfalls or dangers of multidimensional scalings. And they're kind of obvious, so there's not really a lot of point to dwell on them. So first of all, weird distance measures are pretty common. So weird. Oops. That is non-Euclidean or something like that. And this makes a lot of complications. Maybe the best, so like I was saying, you don't know the number of dimensions that were used, but you also don't know how the distance was calculated from the number of dimensions. And it's not unusual for a pretty odd method to have been used. And so that's a complication with multidimensional scaling, that weird distance measures are actually a lot more common than you might think. And so, trying to somehow nail this process and predict the best X there's this wide open space of weird distance measures you can explore. And sometimes they're pretty counterintuitive and sort of problematic. Another thing is that errors, or like a measure of success, these also can be kind of weird and hard to understand. Also, so I'll just put weird. We'll come up with some pretty explicit measures of success, but it's easy to kind of, they can become tricky, and the space over which you can define them is pretty broad, and so it's easy to kind of make trouble for yourself by maybe choosing a bad one or something like that. Okay, so now we're going to dig into some of the details, and we're going to focus on a very specific type of multidimensional scaling called classical multidimensional scaling. So classical MDS. And this goes actually by a bunch of different names, and so I'll just list some of them here. I don't think I even know all of them. So also called, or AKA, principal coordinate analysis. And this has a good reason for it. But that is so close to the acronym for principal component analysis, and even just the words, that it's a little bit of a touchy phrase to use. But so when people use it, sometimes they call that like PCO, right? So for principal and then CO for coordinate analysis. Or sometimes people call it PCO and then like a little A afterwards. To remind you that it's principal coordinate analysis. I don't know, but these are just different names. But there are other names for this. I think I've seen it named after people, like so-and-so's scaling method or something like that. There's lots of different names. The name's not really important. Let's try to understand what exactly is this scheme, okay? And so here's the idea. Okay, so let's say that D, so the following things we're going to suppose are kind of, well, let me just make a little statement here. So the distance matrix D and the distance measure and P, so like the number of variates that went along with whatever this mythological or perhaps real X was, these are actually not enough to determine X. And that's a lot to have, actually. To determine a unique X. And that's almost everything there. The distance measure and the number of variates and the distance matrix itself. But that isn't enough, and there is kind of no way around this. And so let's just do a quick little example to see why this is. It should be pretty simple to understand, I think. So let's suppose that you had a 4x4D, right? So let's say you had a 4x4 matrix for distances. You were told that the distances were Euclidean. Like this could be one that was really just constructed from a data matrix, and you were told that the number of variates in the distance matrix was 2. Right? So, is that enough to determine x? It's not, and so let's just see why. So let's draw so 4x4 means there's 4, so that means n is equal to 4, so there's 4 observations. So let's just draw them in our kind of like fictional space here. So there's 1, 2, 3, and 4. So there's 4x4. I'll put this guy on a different line, like that. And let's say, so okay, these things were Euclidean. I think I used orange for that before. Oops, I always do that. And so you know this distance because it's in D. You know this distance. You know this distance. And you know this distance. And then there's these 2 other ones. This diagonal one here. And then one that kind of goes from here. Oh, it's probably badly drawn. Anyways, you get the idea. So those 6 different distances are known. Those are what are in the distance matrix, and it's Euclidean, so it's symmetric. There's no directionality to the distance. And then suppose that you try to ask yourself, like, what's the best coordinate system to kind of describe this thing? And you immediately run into troubles, right? So suppose you say, okay, well, I'm going to put my axes over here. This is p equals 2, so there's only 2 dimensions, right? So I put my axes right there. Okay, fine. Well, what about here? What about those axes? Or how about these axes? Or let's say, you use a really weird one. I'm running out of colors here. I guess I'll use dark green. It's not even orthogonal, say. So there's 4 different types of axes you could use to describe those data points. And I think if you think about this, you should be able to see. So look, so for all 4, for each axis, you get a different n by p data matrix. But you get the same distance matrix because of the way the geometry works, right? All you care about are these distances, those little orange lines. Those little orange lines have the same lengths no matter how you measured them. If you use the green axes, you get the same thing as if you use the purple ones, or the gray or the black. So there is no one data matrix to go back to know for sure it's the right one. There isn't, So this is kind of an issue. So how do you get around this? So it's really, there's just like this degrees of freedom here, kind of, that you need to kind of swipe away and focus on the kind of key pieces. And so here's what classical multidimensional scaling does. So classical MDS resolves this problem by adding some constraints. Right, and here are the constraints. So first of all, well, the first one is not really a constraint exactly, but we'll say that P is not specified. In other words, it's a free parameter. So to do classical multidimensional scaling, you have to specify the number of dimensions that you think the data matrix had, or number of columns, and then you go from there. So you'll have to play around with this to decide what's the best P. That's up to you. You have to have some scheme for that. It assumes that the distance matrix is Euclidean. That these guys are Euclidean distances. All right. And then the last two are kind of, I think, the most important here, or at least the things that make it kind of interesting. You choose the origin and the orientation of the axes, because that's kind of what you have the freedom to do here, right? Like I could just say, oh, move this guy somewhere else, or can I grab any of these guys? Oh, I can't. It needs some kind of, never tried this. Let's try this. There we go. You could just move this wherever you want, right? So that's changing its origin. I don't think I can, oh yeah, look at that. Or changing its orientation. I can do all those things, right? And so the way that classical multidimensional scaling does this is it has a scheme for choosing the origin and the orientation. It chooses these to be those from principal component analysis. Okay, so what does that mean, right? So first of all, it means that you put the origin in some place so that the X matrix is centered. So X is centered. And that gives you a bunch of constraints. That says that the sum over I equals 1 to n of X row I column K is equal to 0 for all K. Let's see, wait. Column K, row I, column K. So that's some. Those are P different constraints there, right? So it centers makes sure that the coordinates are done in such a way that the data matrix is centered. That's one of the PCA criteria as well. It also requires that the covariance matrix for the data matrix. So if you made some kind of sigma, right, it was 1 over n minus 1 X transpose times X, that this is diagonal. And it's diagonal in principal component analysis, remember, because the principal components are uncorrelated with each other. And so all their covariances are 0 if you're looking at two different axes, two different principal components. Right, and so let's just write that out a little more detailed. So this means that the correlation or the covariance of row I and row J is equal to 0. Another way to say that is the sum of xki, xkj over k is 0. Another way to say it is that, oh, I should say this covariance is 0 if I is not equal to j. And the same thing is true here. Another way to say this is that the dot product of the two columns is 0. So column I, so there's supposed to be a capital X here. That's what's supposed to be here, dotted with capital X, J. So these two different columns is 0. Again, if I is not equal to J. So those are 3 different ways to say the same thing, or 4 different ways, I guess. But so these are a bunch of different constraints, so this is what classical multidimensional scaling does, right? And so you can see, I think you can see, at least I hope, that the reason for the name principal coordinate analysis comes from this fact. So in essence, we're putting the distance matrix into a data matrix, and that data matrix is like in its principal component frame of reference. And so the axes, maybe it makes sense to think of them as the principal coordinates, or I don't know. But so anyway, so that's the origin of the name, the fact that principal component analysis is so closely linked to this. All right, so now I want to go into some kind of mathematical details, some technical details of classical multidimensional scaling or principal coordinate analysis. And, you know, so it's going to get fairly mathematical. But so let me write here. So technical details. Of PCO, or in other words, classical multidimensional scaling, which I'll just call PCO because it's sort of easier to write. Okay, so the idea here is, what do I want to say? If I want to fully understand PCO and kind of everything under the hood, I want to know, how do I use the constraints the ones I just listed, to define some scheme to go from D to X. Right? I want to see explicitly, like I want formulas in the end. Because, you know, I want to code this up or something like that. And so that's kind of the goal of looking at these technical details, and it's going to get fairly mathematical. And I want to say in advance that it's sort of incomplete. The main reference I've been using for this, like I said, is the Everett and Hawthorne book, and it's pretty good, but there's some holes in its description of how this works, but it's kind of the best description I've seen, even with those holes. And so I'm going to call this sort of just a sketch and challenge. Challenges. Right, so I think it would be fun to kind of fill in some of these details. I haven't filled them all in myself, and I won't expect that you have mastered them, but I think it's fun to try to do them. So I want to show you kind of the closest I can get to a full picture of the kind of the under the hood of what happens with PCO, right? So the overall scheme, what we want to do is we want to have some scheme to go from the distance matrix to X. Oh, and I just want to pause. Before we get further into this, the main thing I want you to get out of this lecture is to kind of understand these statements here. What classical multidimensional scaling is doing. So it's coming up with a scheme for going from D to X. And the way it gets around the fact that there's all these freedoms here is by enforcing a bunch of constraints. And these are the constraints here. Basically, it assumes Euclidean distances are what are being described by the data matrix, and it has a scheme for picking the origin and the orientation. And that scheme is the one that lands you in a principal component analysis frame of reference. So those are the pieces. And if you understand that, then you understand what is most important for kind of making use of classical multidimensional scaling and understanding what it does. But so this bit here, I think this is if you really want to kind of dive in and see some of the mathematical details, some of which are kind of cool. Okay, so now first thing I want to do here is to define a new matrix. So I'm going to define a matrix of dot products of the rows of X. right? And I'm going to call it B. So B is going to be, as a matrix, it's written as X times X transpose. Now don't confuse that with the way the correlation matrix, or so the covariance matrix is written. So that Bij, this is the dot product of rho I with rho j of X. The only way you can tell that that is a row rather than a column is that it's supposed to be my lowercase x. So I hope you can tell that. Okay, so a couple things to note here. So notice B is a symmetric matrix, so that's powerful. Right, so what that means is also it's n by n. Right, so that's one difference from the covariance matrix right away that has to do with the fact that these things are in the opposite order. So this is n by n rather than p by p, but it is symmetric. So if you take its transpose, you get itself. And you can see right here, Bij is the same as Bji because dot products are symmetric. Okay, and so the other thing I want to mention about this and remind you, I've just done it like 3 times now, is that B is not the covariance matrix. Or rather, it's not just n minus 1 times the covariance matrix, right? So that is to say, Bij is this dot product of the rows, whereas sigma ij is 1 over, it's a scaled version, n minus 1 over n minus 1 of the dot product of the columns. Right, so these are not the same. I'd only want to mention it because they look so similar, X transpose times X, compared to X times X transpose. It's easy to sort of think they're the same thing. But yeah, so they're not. Okay, and so here I want to show that the following is true. First I'm going to show you that the constraints, we'll use the constraints to show the following. The constraints enable us to do the following. We'll find a way to go from B to D, but also from D back to B. And then we'll finish off by showing how do you get from B to X. All right, so that'll be our whole scheme. All right, so I have 2 things to prove right now. One is how do you go from B to D? This is not really so necessary, but it's easy, so I'm just going to show it. And the second thing, which is more interesting, is how do I get from D to B? And that second thing is interesting because I want to know how to get from D to X, ultimately. That's the plan. So I'm going to go from D to B and then to X. Okay, but so first let's do proof of 1, which is pretty easy. Right, so I just want to have some scheme for going from B to D, and I don't even really need to use any constraints for this. Right, so the distance matrix, Dij squared, this is supposed to be the Euclidean distance between observation I and j. So that's rho I minus rho j as vectors squared. And that means that difference dotted with itself. And so that's equal to the magnitude of xi squared plus the magnitude of xj squared, and then minus twice the dot product of the 2. Right? And so we can translate this. If you look back at what was B, how was B defined? Right? So Bij is the dot product of xi and xj. So xi squared is the dot product of xi with itself. So that's Bii. Xj squared is Bjj. And then this guy is minus twice Bij. Right? And so that's how you go from, if you were given the B matrix, then all those dot products, then that's how you would make D. Again, that's not particularly interesting, but it's easy to show. And so let's now look at the proof of number 2, which is harder. And there are holes. or challenges, I should say, which I think are fun to work with. Okay, so now here's the idea. So remember, we have some constraints, right? So if you have these constraints, I'm going to list one of them. The centering of the data. If the following constraint holds, which we wanted to, and if you defined the trace of the matrix B to be T, that's just a definition there. So the first thing is if you have that constraint, and the second one is just a definition, then, and this is a challenge to show, first challenge, this one is the more doable, then the following is true. 1 over n times the sum. So what I'm doing is I'm making a sum. I'm going to look at a bunch of different sums of this defining relationship for B. Where do I have it here? I'm going to make a bunch of sums over this expression. I'm going to make a sum over I, then I'm going to make a sum over J, and then I'm going to make a sum over both I and J. And for each one, I'm going to take a different expression. So I'm going to get 3 different expressions here. So the sum over I, and this goes from 1 to n, and I'm scaling each of them by 1 over n accordingly, of this guy, Bij. If I do that sum, then what I'll find is 1 over n times the sum over I equals 1 to n dij squared is equal to, and I'm just going to define a symbol, dot j, where the dot means you're summing over that. This is equal to t plus n times bjj. Right? So really this is kind of just defining this symbol here and claiming that the sum turns into that, and that you can check. That's the challenge. Okay, now the next sum is a sum over j. And again, a weighted thing. And it's d squared ij is equal to di and then a dot squared. That's just the definition. And this is equal to t plus n times bii. All right, and so then the third thing, this is when you do the sum over both indices. So this is 1 over n squared, sum over I, and sum over j of bij. And again, this, I'm finding all this by summing over this thing. All right. I should say actually here, yeah, I think what I should say here is actually just the following. No, I'm not summing. These are not what I'm summing. These are the d's. That's where I'm getting these expressions from. So this is 1 over n squared, sum over I, sum over j. This is just the defining thing. And so this I'm going to define it as, I'm going to define it as d dot dot. Dot just means you sum over an index. And this thing is equal to 2n times t. Okay? So that's the first challenge, is to show that these things hold, right? When you enforce the centering condition, right? It's not, I wouldn't say it's super easy, but you should be able to do this one. And then the second thing, so then, and this I think is a bigger challenge. And remember, I'm not going to expect you to be able to do these. I just think they're kind of fun. I wanted to show you as much as I could, as much as I was able to dig up myself. And for this, I think you might need to use the fact that sigma is diagonal. So I'll put that off to the side as like a suggestion or a hint. If you do that, then the following is true. Then Bij can be written as -1/2 dij squared minus di dot squared minus d dot j squared plus d double dot squared. Okay, so those are pretty challenging things, I think. But if you were to show these, and again, I said there were going to be some holes in this, and these are probably the two biggest ones, then you've now got a scheme for going from D to B, right? And now why do I care about this? Because the whole point is, so our scheme is to do the following. So we go D to B, and then we compute X, right? And so we just need some explicit rules for how to do it. And I've got now some explicit rules for how you compute the B's. The formula is written right there. Even if you don't show in the proof how to do it, you at least you could do this, right? You could compute those B's. If you trust me that that's right, you could certainly do that. And then how do we get from the B's to the X, right? So how do we get from B to X? All right, so here we go. Here's how it works. So we say since B is symmetric, which again I say is powerful, since B is symmetric, so what is the most powerful thing about that when a matrix is symmetric, I think? Well, what I think is the most powerful thing about it is that it means the matrix is diagonalizable. And I'll remind you what that means. We came across this, I think, pretty early on, maybe in lecture 2 or 3, I can't remember. So this is what this means. You should probably go back and read that again if you don't remember when we first encountered it. But it's essentially what I'm telling you here. It means that you can write B in the following way. You can write it as a product of 3 different matrices, V, L, and then V transpose, where the following is true. V transpose is actually the inverse of V. L is equal, I'll move this over here. Oops. Oh, I forgot I had that on that. Right, L is a diagonal matrix, hence the term diagonalizable, really, of eigenvalues. Potentially n non-zero of them, if it's full rank. And what does the V matrix look like? Right, so the V matrix looks like this. It's built out of the eigenvectors of B. Like that, okay? And so these are the eigenvectors, meaning, so where B times V hat I is equal to lambda I V hat I. And you can choose to order them in the usual way that we've been doing in terms of decreasing absolute value of eigenvalue. But so This is just, I'm just telling you B is diagonalizable, okay? So it can be written like this. In terms of it, you can deconstruct it. Sometimes I think this is called spectral decomposition or something, where you can deconstruct it in terms of its eigenvectors and eigenvalues, which is useful for a bunch of different reasons. But so let's do that, and then I'm just going to claim, and we'll prove this little claim. It's quite easy. That you can write x as follows. X is equal to v times L to the 1/2 power, where L to the 1/2 power, remember L is diagonal, so raising it to a power is easy. Like that, right? So that's a claim, and if it's true, if this is true, then we're done, because we know how to get from D to B. Again, there were some holes in there. And now you know how to diagonalize B. You just write it in you find its eigenvalues and eigenvectors, and then you write these matrices L, V, and V transpose. And then apparently X is made from the eigenvector matrix V and the square root of the diagonal matrix. Okay, and so let's just prove it. So proof, or check. I'm going to check this by showing you that X times X transpose gives you B, which is what it should. Okay, so X times X transpose is V times L to the 1/2 times V times L to the 1/2 transpose. And now we'll take the transpose, and the transpose, you switch the order and then do the transpose. And the transpose of a diagonal matrix is the diagonal matrix. Like that. And L to the 1/2 times L to the 1/2 is just L. And I get that. But that's the definition of B, right? In terms of that matrix, V times L times V transpose. So this is B. And so this proof is kind of done. So we've shown how to get from D to X in principle, with a little bit of holes in the details. So you might be kind of wondering if some of it's true. Like I think, for example, for me personally, I'm not trying to be like sneaky here. I also find it kind of like, I want some more information here. Like, I think this is the place where you have to use the second piece of information for the principal component frame, the fact that the covariance matrix is diagonal. I think that's where you need to do it. But even if you didn't do the proof and you didn't fill in the holes, you could in principle, just if you wanted to, you could code up principal coordinate analysis now, because you know how to go from the distances to the b's, if you trust this equation. And then you know how to go from the B matrix to the X matrix. All right, so that's the introduction to classical multidimensional scaling, or your first sort of taste of how you can transform from distances to observations when you don't really know all that much about the nature of the observations. In the next lecture, we're going to try this out, and you're going to see some code in R and how it works. You'll be able to do it yourself, and you get some impression of how to assess how well it worked, and so on. I'll see you then.